Okay, now for some developmental background to the science of electricity. I break it up into about 5 phases, and the first one is a period of time from the 1750s to the 1800. Single fluid theory, established by Ben Franklin, and also a lot of terminology also established by Ben Franklin. And this is from the period, and not all by him, but it was from the period of 1750s, say, to 1800. And then the next phase would be continuous current, where instead of working with static discharge sparks, there was a method developed to provide a constant current, and that's what we know of now as the battery. It's a chemical process. And then the third phase, and that was 1800 pretty much, and then the third phase would be magnetism in the 1820s roughly. And the fourth phase would be Ohm's law, which went largely unnoticed for almost 20 years. And then the fifth phase, circuit analysis. There's the hints of beginnings of it, the focus on it, but Ohm's law wasn't quite utilized for about 20 years later, within the 30s or 40s. So deleting that, we begin with the first developmental phase, which is the period of time from the latter half of the 1700s. And it's a single fluid theory, as mentioned before, and a lot of terminology came up during this time too. And much of it is coined by or applied by Ben Franklin. First of all, not the least, is the plus and negative, plus and minus, which is pretty much the direct, is a direct description of the single fluid theory. In addition, he came up with words like charge and discharge, coined after the charging of a gun and firing it, discharging it. Conductor, condenser. Condenser applies to what was called back then a Leyden jar, and what it would basically do is take the static charge that was on a glass rod, let's say, from rubbing a silk with it, touching to that, and it would condense the charge, make it compact. And we still call them today that, but also the more common name for that is called capacitor. And here's the schematic symbol that you'll see eventually for a capacitor. Battery was another phrase he came up with, but that didn't apply to exactly what we thought it as we do today. It was more or less applied to a bunch of condensers, things that could be charged like a bunch of guns, and a battery of guns. So it's kind of like a battery of marksmen or a battery of soldiers. So it was applied to a bunch of condensers, Leyden jars, connected together. He also came up with the term armature, or these are all terms, but he reapplied them to electricity. Armature and tension. Armature was applied to initially, now it's applied to motors, but initially he applied it to the hard surface around amethyst. Around what the heck? Oh no, amber. Around the hard shell around amber. And in tension, he applied to experiments where you would have a charged surface, and then there would be ropes connecting to little balls or little orbs, metallic orbs, and the rope would be insulator, and they would develop to the same charges, and they would repel, and they would apply tension to the cord connecting the two charged items. Okay, moving on to the next phase, continuous current. Continuous current more or less was started by Volta when he invented what was called a zinc pile, but previous to that, he came up with that from an earlier experiment conducted, or observation and then eventual experiments, by Galvani in about about 1888. He more or less observed that these hanging frog legs from this fence, iron fence with this copper ring apparently, when an electric field was generated by the lightning, it would cause them to twitch, and he came up with a hypothesis of animal electricity, which isn't all that wrong completely, but it wasn't the main source, or it was a combination of all three. He focused on the animal, where Volta focused on the two different metals. He said it wasn't so much animal electricity as much as it was caused by the two different metals. So he thought, well, I can repeat what he saw, and he came up with the zinc, what he called the zinc pile, which were basically tablets of copper and zinc sandwiched around like animal grease or brine or something like that to simulate the frog electrolyte. And then when he did that, he was able to observe a voltage. So he came up with what we now call the battery. The next phase in the development of electricity as a science began around the 1820s, and that was magnetism. In 1820, a scientist named Ørsted was teaching a class and was running an experiment, running a current through a wire, and he noticed he had a compass nearby, and he noticed that every time he turned on the circuit, that a current would flow through the wire, that the compass would all of a sudden jump in a particular way. So he more or less discovered magnetism, or the magnetic personality of electricity. When you have a current flow, you're going to have a magnetic field developed, and it develops in circles, concentric circles, or not concentric, in circles around the current going through a wire, and then the field goes in circular motions around that wire. Ampere, around 1827, did extensive work and study and came up with elaborate equations, more or less, but he more or less came up with equations with the relationship between current and the magnetic field. Let me see, where's these? You can more or less say, so they started what might be called this. You could start saying the initial beginnings of what the schematic symbol that we have now for an inductor. I can draw this horizontal or vertical. I chose horizontal for some reason this time. And before I move on, the previous slide we talked about the battery. That schematic symbol looks something like this. So that ends this phase. The fourth phase establishes the beginning of Ohm's law, which is basically the equation of electricity or circuit analysis. In 1827, he was doing some studies on heat transfer and came up with these relationships. Basically, the voltage equals the current times the resistance to the flow of current, the single flow of current. Resistance can be also figured by the resistivity of the material times the length divided by the area. This wasn't really that much appreciated for about another 20 years. He was primarily focused on the heat study, and it really wasn't grabbed onto for circuit analysis pretty much about 20 years later. Let's correct this study. The schematic symbol for a resistor is this. Alright, well, I draw them like that. The more common way to draw them is a few squiggly lines. And you can draw them horizontal or vertical, but that's the schematic symbol for a resistor. Okay, the next phase is when circuit analysis just started to develop. In, I believe it was 1830, pretty much. Faraday and Henry came up with the same observation and law, if you will. Faraday, they were basically the law of induction. We saw previously in magnetism, when you have a current going through a conductor, that magnetic fields develop around that. If you have a changing magnetic field, you'll develop a current. So that was the beginnings. Ohm's law wasn't really quite appreciated yet, or just maybe starting to think about applications of it. And around this time, the generator, the motor, and this telegraph started to spark the idea of circuit analysis. Then around 1845, we start to get, this is where it takes off, or begins to really take off. Kirchhoff's law, and basically it concerns voltage and current in different circuit paths. The current and voltage law, it's called. More on that later. And then we have Thevenin's theorem, which he came up with in 1883, but it was pretty much observed in around 1850s by other scientists. But he revived it and popularized it. And basically it's a theorem to simplify circuits for analysis. It's a circuit simplification. Equivalent circuits you can draw from more complex circuits. And Hertz, he was around 1880s also, 1880s. And he was he pretty much came up with the very beginnings of what we call radio. And it was basically, let me enlarge this. Let me see if I can enlarge this. I'll enlarge this. And then keep that other one small because this pretty much explains that. Let's see. He had an apparatus, and you can see this. I put this in the circuit analysis portion because you can start to see that they're starting to look at circuits more seriously. And here he has what developed around that time was what we call an inductor, coupled magnetically with another inductor to form what we call a transformer. There's a capacitor to control the current and voltage changes. And then there's a gap here, and basically it breaks and opens the circuit, and it develops a high voltage on each of these terminals and causes a spark. It's called the spark gap filter. And then by using a ring with 2 electrode balls at the end, he was able to transmit a spark, opening and closing the circuit, and it would see the spark through the airwaves, if you will. On this thing, it would develop a spark on this. So that's pretty much the beginnings of radio. Okay, I went through the 5 key phases as I divided it and ended up with circuit analysis. And as we do that, we enter the 20th century, 1900s. Around the turn of the century, Edison and Tesla were big in power transmission. And then we have like Thomson, Rutherford, Bohr, around the 1910s, where we pretty much refined the atom. Thomson, as I mentioned, like electrons and positive and negative charges is related to the atom, really wasn't thought of until around Thomson, when he combined the electric theory kind of with the atomic theory, and said each little bit of atom element consists of electric charge. These are the subatomic particles, if you will, electric charge and positive charge. Before that, it really wasn't thought of much in that way. In fact, during the days of when the battery was being invented, the atomic theory started taking off, but it didn't really include negative and positive charges so much as it did atomic weight, elemental weight. And they divided up the periodic table quite far. And then as they refined their understanding of the atom with Thomson, where he said, well, they consist of positive and negative charges. Each element has a certain clump of positive and negative charges. Rutherford came along and refined that further and came up with a nuclear model, and Bohr refined it even further with the Bohr model, quantum theory. And that's where that's where the next topic will be. The module will discuss the atomic theory and its relationship, because as I mentioned, back when the atomic theory was revived around during the period late 1800s, around the turn of the 1800s, and it was but it didn't include the positive and negative charge, or the atomic theory as we look at it today. It was basically just based on weights and masses, and they were able to come up with a periodic table and some observations, and then it got further refined by Thomson, Rutherford, and Bohr around 1910s, where it became the nuclear model, where you have a certain amount of protons in the nucleus and a certain amount of electrons going around it, orbiting it. So then after that, pretty much for the next up to the 1950s, let's say, up to 1950, we pretty much have the development of the solar cell, the diode, the vacuum tube, and then the transistor, which is basically the vacuum tube. It replaces the vacuum tube. Okay, that's it for now. Thank you.